Well, thank you to Robert and all of the organizers, of course, for giving me a chance to speak today. This is a great pleasure. Of course, I would much prefer to be in Marseille, but we all would, I'm sure. But this is a nice way to get together given the circumstance. And I also, since I have my colleagues from Debrecen here, I want to say hello and thank them also for the years of collaboration and inspiration they've given to me. I took a little bit of a break from research for a few years being a father. So in the last 2 years, I've returned to doing research, and I'm learning a lot from this conference and from other conferences over the last 2 years. And have a few things going on research-wise that I'm going to talk a little bit about today. I had some interesting conversations with Paul Voutier and Michael Bennett and Andrew Granville, and so there's a lot of interesting mathematics going on that I'm trying to contribute to. I feel bad for Mike Bennett right now. He's dealing with a fiasco at his university, so I wish him well if he's anywhere in touch of this. But I just wanted to mention that I really hope that, you know, some aspect of this talk will be of interest. A lot of it is not very highbrow. It's very hands-on. I'm trying to solve Diophantine equations in various ways. And so I hope this talk will be of interest. Let me move along to the next slide and mention that some of this work, or most of it, is joint work with Michael Bennett. And at the end of my talk, I will talk about something which is joint work with Pingzi Yuan from the People's Republic of China. So in this talk, I'm going to talk about index form equations. They come up in a very natural way when one is trying to compute power integral bases of number fields. This is a very large subject. We're not going to cover this entire subject. We'll be very interested in one particular area of research in this topic. In particular, what I want to look at are pure quartic fields. And when trying to compute power integral bases of pure quartic fields, a family of Thue equations come up. And so what we're trying to do is completely solve this family of Thue equations. And in particular, what we're able to do is provide a different approach to solving this family of Thue equations than the methods that have been given in the past. So that will be the main thrust of the lecture, this part. But since there are other things to say about this problem, I will continue and talk a little bit about how it is very closely connected to the Abc conjecture. Eventually, I will talk about a related family of elliptic curves, like I said earlier, and this last part of the talk is joint work with Pingzi Yuan. Okay, so without further delay, let me start off by looking at the source of index form equations or index forms. Where did these things come from? Well, let's look at an integral basis of a number field K, and I'll just write it as 1 omega 2 up to omega of n. And I'm going to look at the linear form on the n-1 variables capital X sub 2 up to capital X sub n. And I'll write that as a vector. So we're looking at the linear form L evaluated at the coefficient or the vector of variables x2 up to xn. This the discriminant of this linear form from the number field k down to q is defined in the obvious way. You look over the automorphisms of, or the embeddings of k into the complex numbers. You look at all the possible differences and square them. So this is the standard definition. And if you do that, what you end up with is a polynomial I of x to the power 2 times the discriminant of the field. And this I of x is the polynomial that we're trying to get our hands on. It's a decomposable form with integer coefficients, and it's obviously of degree n times n minus 1 over 2, where n is the degree of the number field k, and this is called an index form. In particular, let's look at what this index form gives you. It gives you a measure of how far away a number will generate a basis of the field. So let's take some gamma in the field k and write it out in the basis x1 plus x2 omega 2 and so on. Then if this element is a primitive element, so if it generates the field, then the value of the index form at gamma is, well, how do you evaluate it? You evaluate it using the coefficients. We're doing it with respect to the basis, so this is what we do. And this number in absolute value is the additive index of the ring generated by gamma inside the additive group of the ring of integers. So in particular, if this number is equal to 1, if we're able to generate the entire ring of integers, then in a way this number gamma is quite special, and very special, and we call powers of gamma a power integral basis. So 1 gamma, gamma squared up to gamma to the n minus 1 is a power integral basis precisely when that index is equal to plus or minus 1. And the problem for a given number field is to find values x2 up to x sub n which solve this equation. And in general, this is obviously going to be a very difficult problem. So let's take a toy example. Q adjoin the fourth root of 2, and well, we'll start with a basis in order to get going. So I'm cheating a little bit, but I'll come back to this basis in a second. So here I'm going to take the obvious basis 1 alpha, alpha squared, and alpha cubed. And with that basis, when you go through the process of computing the discriminant and looking at the index form that comes out of it, what you get is this polynomial of degree 6 in 3 variables, x2, x3, and x4. So a priori, in advance of knowing anything, if we need to compute a power integral basis of this simple quartic field, then we would need to solve the problem of this polynomial equal to plus or minus 1. Now, solving a degree 6 polynomial equation in 3 variables like that sounds like a pretty difficult problem. So, solving this equation, I evaluated x2, x3, x4 equal to plus or minus 1. Non-trivially is obviously a very difficult problem. So trivially, we can solve it if we set x3 and x4 equal to 0. Then we have x2 equal to plus or minus 1, which gives us the trivial basis here. Okay, but we want to know if there are other power integral bases other than the trivial one. So in general, if I replace the number 2 by any positive integer, or any fourth power free integer or a square free integer, how are we going to go about solving the equation I of x equal to plus or minus 1? So the way to get around this difficulty comes from a beautiful lemma by three people, Istvan Gal, Attila Peto, and Michael Post, proved in 1993 the following fundamental result, which appears in many papers and is extremely useful for this purpose. So let me start by giving the setup of this lemma. There's a lot on this slide, so I want to just present it a little bit at a time. So here we have a quartic number field, Q adjoins psi, and the polynomial is some generic quartic polynomial. And I is the index that we defined earlier with respect to this basis 1 psi, psi squared, and psi cubed. N will be the value of I at psi, and M will be the minimal positive value of the index over integer inputs to I. Then we are going to need the cubic resolvent of the polynomial f sub psi, and I'll just write it as capital F of uv, which I can write in terms of a1, a2, a3, and a4 as follows. I won't read that off. And also in this lemma, there are two associated polynomials, q1 and q2, in three variables, x, y, and z. Again, those polynomials are defined completely in terms of the coefficient of f sub psi. And with all of this in place, we get the beautiful result below. So if you have some integer phi in the field, now capital D will denote the denominator of phi. So here phi will generate a power integral basis. If it does, then there is an integral solution uv of f of uv equal to plus or minus this denominator of phi to the power 6 times little m times little n, where u and v are given explicitly by the polynomials q sub 1 and q sub 2. So we use this lemma to go from where we were on the previous slide, almost in a hopeless situation, to now we're having to solve a Thue equation, basically. So we can do this computationally. And what I'm interested in specifically are pure quartic fields. So if I look at the field x to the fourth minus d, defined by the polynomial x to the fourth minus d, here psi is going to be the root d to the 1/4. Then this, as I showed earlier, because of the trivial solution to the very complicated equation of degree 6, we get that this is an integral basis precisely for d bigger than 1 in absolute value and d congruent to 2 or 3 mod 4. This comes from some work of someone else, another group that I'll mention in a second. But let me get to the main point here, that now, because of all of the other coefficients being equal to 0, the polynomial f that I defined on the previous slide becomes considerably simpler. In particular, it's simply u times u squared plus 4dv squared. And the other polynomials, q1 and q2, also become extremely simple. U is given specifically by x squared minus dz squared, and the value v is given by y squared minus xz. So that's a simple computation to get that. So what does that say? Well, if we go to the lemma, it says that our phi if this generates a power integral basis, then d is equal to 1, the denominator. The values of m and n are also equal to plus or minus 1. So by the lemma, that gives the value of the Thue equation being equal to plus or minus 1. And if you look carefully at this, here I really want d to be bigger than 1. So I put in absolute value by mistake there. So here d is positive. We have a positive definite form. And the only way you're going to get plus or minus 1 on the right-hand side is if this value, these are both plus or minus 1. And of course, that implies that v is equal to 0 right here. So you get that u is equal to plus or minus 1 and v is equal to 0. So this really nails down the possible values. So here, this is what I've written u, which we know is x squared minus dz squared equal to plus or minus 1 v, which is y squared minus xz, is equal to 0. Now, this equation right here, x and z are co-prime from this equation. So that says that these are both squares. So what I'm going to do is label little x to be capital X squared. And I'm going to label little z to be capital Z squared. And I'm going to plug those into this equation right here. And at the end of all of this analysis, what we get is this quartic equation. So this is really going to become the main topic of the lecture, is this quartic equation right here. So what we have is, if you have a power integral basis generated by phi, it really has to look like x squared d to the 1/4 plus or minus xz d to the 2/4 plus z squared d to the 3/4, where x and z come from a solution of this quartic equation. So for example, so this is the result I mentioned briefly earlier. It was a result of Ahmad, Hamid, Hussein, and Nakahara from 2011, and they showed that for arbitrary d conjugate to 2 or 3 mod 4, then you always get an integral basis from the trivial solution of the index form equation. So this set of numbers is a power integral basis. So this is kind of the trivial solution to our problem, but there are non-trivial solutions to the problem. So for example, if we look at d equals to 15, we go to our quartic equation right here, we see that there's a solution with x equal to 2 and z equal to 1. And so we can just write down a generator of a power integral basis using the values x and z. So there it is. So it becomes a very simple process to find these non-trivial generators of power integral bases using the lemma of Gall, Peto, and Post for this family of fields. So this has been worked on by a few people. Let me talk about some computational results that have appeared in the literature on this problem. There's some really nice work by Attila Berthes, and I don't know the fellow Basso, and Kalmanjiri and Akos Pinter in 2010. They were able to completely solve this Thue equation for d up to 400. And in the same work, they were able to solve it for d up to 2000, provided d is odd. And I should mention that in this paper, their work is not specific to the case of degree 4, the equations of degree 4. They prove results for all n using modularity of elliptic curves and Frey curve methods, and it's a very, very deep paper. I'm only talking about the work they did to deal with the degree 4 case here. So one should keep that in mind. That wasn't the focus of their work. This was picked up again by Istvan Gall and Laszlo Remete, and they were able to find all small solutions in a very efficient manner for D all the way up to 10 to the 7. And I'll just say a few words about the computations that were done. My understanding is that the 2010 computations used a combination of magma and, Paris for solving Thue equations. And I think most of us at the conference are well aware of solving Thue equations with large coefficients becomes very onerous. It's very time consuming. The bounds from linear forms and logs can be very large. Computing units in quartic fields becomes very labor intensive, and so on. And the L cube reduction process might not give you a small enough bound, so your exhaustion may be over a very large space. So this was probably quite a bit of work to do this. And similarly, in 2018, I believe they used cache on a high performance computer, and the algebraic numbers that came up in the computation had thousands of digits and required quite a bit of computation to get that work done. Okay, let me get to what I want to talk about. My contribution, or with Mike, is we looked at this paper of Istvan Gall, and it's a beautiful paper, but we had an idea that came from an observation. So the observation is as simple as you can get. It's if you have integers x and y satisfying this quartic equation, then x squared plus y squared is a unit in this ring of integers, obviously. So, well, what does that give you? It surprisingly a lot. So let me just mention quickly some more in the way of some observations we made early on in the process. So here, epsilon sub d will denote the fundamental unit in the ring z adjoin the square root of d. And I'm going to list off some d for which this equation is solvable. So here, the first one is 2, and the solutions are 1 and 1, x and y both equal to 1, which gives you the unit 1 plus root 2. And lo and behold, it's the fundamental unit of the quadratic field. Okay, well, maybe that always happens. Maybe it's always the fundamental unit. Who knows? It's just a question. And the second example is 3 squared plus 2 squared times the square root of 5. And well, no, it's the square of the fundamental unit. So maybe this isn't true. Well, let's look a little further. And if we look at 15 and 39, in those cases, we get the fundamental unit. So there seems to be a possibility that whenever you have a unit of this form, or whenever you have a solution to this Thue equation, you're really looking at the fundamental unit in this ring. Well, we did more computation with the table from the paper of Gall and Remete, and for all cases different than 5, it turned out that the unit that one gets from the solution of the quartic Thue equation does in fact give you the fundamental unit in the ring z adjoin the square root of d. So, okay, maybe we ought to try to prove this thing. And in doing so, it turned out to be a pretty straightforward thing to do. So here is the theorem that I want to state. So if d is a non-square positive integer, and assume there exists x and y satisfying this quartic equation, then in fact x squared plus y squared root d is the fundamental unit in the ring z adjoin the square root of d. except for d equal to 5, in which case we just saw that it's the square of the fundamental unit. And the proof is very simple given the tools at our disposal. So in order to prove this, we use two beautiful theorems of Wilhelm Ljunggren and another beautiful theorem by Chen and Voutier. Let me just run through that rather quickly. So the proof of the theorem uses this amazing result of Ljunggren from 1942. I've mentioned this in several papers, and I'm probably his biggest fan. So these theorems should never be forgotten. So I'll just state them one more time. So d here is a positive non-square integer. Epsilon sub d is the fundamental solution of the Pell equation, x squared minus dy squared equal to 1. And for k bigger than or equal to 1, I'm going to represent the kth power of the fundamental unit or fundamental solution as t sub k plus u sub k root d. So you get two sequences, t sub k and u sub k, generated by taking powers of this unit. And what Ljunggren actually proves, he doesn't state it this way, but what he actually proves is there's at most one odd index k for which t sub k is a square. There's at most one index congruent to 2 mod 4 for which t sub k is a square, and there are no indices congruent to 0 mod 4 for which t sub k is a square. That's actually how the proof works, what it gives, and which is, it's surprising to me how much work went into this. The proof is very complicated, it's very long, it's very sophisticated. It used Stolem's method. It's hard to follow this work unless you really, you know, get your hands dirty and follow this. And it's surprising to me, the natural question that comes up when one reads this theorem is, okay, which value of k? So if there's only one odd value of k, then which value of k is it? And one would immediately think, would it be k equals to 1? And if you do just a little bit of computation, you really don't need a computer at all. So Ljunggren could have asked this question and could have tried to prove it. It's surprising that he didn't prove it himself, that k would be equal to 1. Similarly, the same proof you think would work for k equals to 2. In any event, this was proved many years later by John Cohn. So I will just state it as a lemma. So if k is odd and t sub k is a square, then k equals to 1. And similarly, if k is congruent to 2 mod 4 and t sub k is a square, then k is equal to 2. And the proof uses a very clever manipulation of Legendre symbols. And it just surprises me that Ljunggren didn't try to prove this himself or even make any mention of it whatsoever in his papers. Okay, let's go back to the proof of our theorem. It's pretty straightforward. If we have a unit which is of the form x squared plus y squared root d, and let's suppose the index is not equal to 1, then by Cohn's refinement of Ljunggren's theorem, we have k equals to 2. Wow, okay, we're pretty close already without doing anything. Now, if k is equal to 2, then we have that this number y squared is u sub 2, and u sub 2 we know we can write from properties of solutions of Pell equations, we can write it as 2 times t sub 1 times u sub 1. So that says that since these numbers are co-prime, t sub 1 is either a square or twice a square. So I'm just writing it as either a square or twice a square when I do that. And furthermore, because of the identity t sub 2 equal to 2 times t sub 1 squared minus 1, we get that the number x squared, which is t sub 2, is either 2r squared minus 1 or 8r squared minus 1. And both of these cases can be dealt with basically one swing at the bat using Ljunggren's famous result on x squared minus 2y to the fourth equal to minus 1. Everyone knows about this, I'm sure. And by applying this result, it actually, we work things back, and the only value of d which we get is 1785. And in that case, the only solution to this equation occurs at k equal to 1. Okay, so this completely solves the problem in the case of the norm being 1. Now, if the norm is equal to minus 1, this is an easier case because it's a straightforward consequence of a very beautiful theorem by Chen and Voutier from 1997, who generalized the result of Ljunggren that I just mentioned. And here, d bigger than 2, so I should say that d is bigger than 2, be a non-square positive integer for which the negative Pell equation is solvable. And I'm going to let xy equal to tu denote the minimal solution of this equation. Then the quartic equation x squared minus dy to the fourth equal to minus 1 has at most one solution in positive integers, and if it exists, it comes from the minimal solution. It's actually equal to it. Okay, so they really solved this problem completely. It's a beautiful result, and that gives the proof of our theorem in the case of minus 1. So we really had nothing to prove. It was a straightforward consequence of results that appear in the literature. Anyway, going back to computing power integral bases by this theorem that we've just stated, determining those values of d for which a non-trivial power integral basis exists, or in other words, when this quartic equation is solvable, we don't need to solve quartic Thue equations. We just need to compute fundamental units in these quadratic orders. Okay, well, I could go ahead and start computing this, and of course I could get a little bit further than 10 to the 7, but there are people who actually make a living doing this kind of computation. So rather than do this ourselves, we've deferred to the champions of this kind of work. And right now, at this very moment, as we speak, CPUs are busy all over Canada computing fundamental units in quadratic fields. And I'm not kidding. This computation should be done in the early new year. This was promised to me by Michael Jacobson. So they have a program underway that will compute a table of fundamental units of quadratic fields for all d up to 2 to the 40. So that's like about 10 to the 12th. So once that list is completed, Mike Jacobson said he would do a favor for us and go through his list and give us all the values of d for which this equation is solvable. So we should get notification of a complete table up to 2 to the 40 sometime in the new year. Well, okay, so as promised, I mentioned that there was a connection to the Abc conjecture. Now, the Abc conjecture goes back to the mid-80s. Joseph Oosterlee first proposed a formulation and later refined by David Masser. And the way I like to read the ABC might be a little bit different than what is standard. I just think this way is more intuitive. So this phrasing of the ABC says that for any epsilon bigger than 0, there are only finitely many triples of coprime integers a, b, and c, satisfying a plus b equal to c, for which c is bigger than the radical of abc to the power 1 plus epsilon. So the quality of a triple is given specifically by this L of ABC, which is basically all I'm doing is isolating the exponent. So it's log of C over log of a radical of C. I don't know where this number L comes from. It's a bit of a mystery to me. any event, there's some rather difficult discussions going on around the world concerning the ABC conjecture. As we all know, there's this work going on in Kyoto, and a friend of mine described this unfortunate situation that inside Kyoto, the ABC conjecture is true. In fact, an effective version of the ABC conjecture is true inside Kyoto, and outside Kyoto, it's not true yet. So everyone can decide for themselves. I believe those that have won Fields medals, so I'm in the non-Kyoto side of things. In any event, we do need, for our purpose, an effective version of the ABC conjecture in order to connect with our problem. This version of the ABC conjecture is ineffective and not terribly useful. So, well, it's useful, but it's not going to completely solve the problem we'd like to be able to solve. Now, let me just mention a few of the top ABC. If you've looked at ABC before, you're probably familiar with these numbers. This is from RaySat, I believe, and these are the other examples. So essentially, as you would expect, all of the numbers involved have small prime factors, and the ABC conjecture says that if you add two numbers with small prime factors, you're rarely ever going to get a number that has all small prime factors. So that's what ABC is all about. But what I said before is we really want to have an effective version of ABC, and this was proposed by Brauken a few years ago. He said that if the value of L or R, whatever the case may be, is bigger than 1.5, then all positive integers satisfying ABC with the value L bigger than 1.5 are given in the table that I just showed. So he used that effective version to prove results, Diophantine results and otherwise. But unfortunately, this conjecture is actually false. So after Brauken published his paper, there was a computation by, I can't remember the name of the person who found this particular counterexample, but in fact, it has quality bigger than 1.5 and not in the table that I just showed you. So one has to be really careful about these effective versions of the ABC conjecture. And my way of being careful is to, hold on a second. Now, I want to mention that there is an updated version of the tables on Bart de Smet's website. If anyone cares to look, you can just Google de Smet ABC and you will find the current version of the ABC table. My way of being careful about these is to throw caution into the wind, and I'm going to state what I call a restrictive effective ABC conjecture, and I'll describe what I mean by restricted in a second. So here, what I'm going to do instead of A, you notice there's a 1 here, so I've replaced C by B plus 1. So here's my A, B, and C. So I've taken away 1 degree of freedom. I'm only going to look at all triples of integers 1, B, and B plus 1. And what I'm going to do is I'm going to be even more ruthless than Brauken. I'm going to change 1.5 to 1.4. And this is my effective version of the ABC conjecture that I'm going to use for the problem that we're looking at. So here, B is a positive integer, R is the radical of B times B plus 1. Then as long as this triple is not in de Smet's table, we always have B plus 1 smaller than the radical to the power of 1.4. So if anyone finds a counterexample to this, I'd love to see it. It could happen. I'm not saying it won't. I'm just throwing it out there for discussion, and I'm using it for my purpose. So in particular, if you have a solution to this quartic Thue equation and you assume the restrictive ABC conjecture, effective ABC conjecture, then in fact, the fundamental unit is really, really small. It's smaller than 2d squared. Remember, in general, fundamental unit is huge. It's e to the root d. So it has like root d, big O of root d coefficients, x and y. So here, having a bound of 2d squared is really small. Well, what does that mean? That means that in order to compute the fundamental unit, we only need to compute a few convergents of the continued fraction expansion. And once the coefficients are bigger than 2d squared, we can break the computation. We know that there can't be a solution to this equation. So my question then about this is, given how much CPU Booker and Jacobson are using to get all the way up to 10 to the 12th, and believe me, it's a lot. If one uses our restricted effective ABC conjecture and through the same amount of CPU, how large could we solve this equation? It would be interesting to see. I don't know if there's any use in doing that, but nevertheless, it's a question. Now, using this idea, we were able to replicate the list of values of D up to 10 to the 7 in about half an hour on my laptop. So the point being that, you know, obviously this is going to be a very efficient way of finding which values of D have power integral bases. And in fact, when I said about what I said about the continued fraction expansion of the square root of D, I looked at the average number of iterations required. Some required a large number of iterations. They may have had a lot of ones in there, a lot of partial quotients, which were ones, but typically we were able to get past the 2d squared bound after 6 iterations on average. So that shows how small the computation is compared to actually having to find the fundamental unit in the quadratic field. Okay, for the last part of my talk, I will go through rather quickly because I see that I'm running out of time. There's a theorem that Pingzi Yuan and a colleague of his, Lin, and I proved, and it has to do with a question that Zagier asked a long time ago. I believe this is from a paper, Large Integer Points, from maybe 1987 or something. Yeah, 1987. And the question he asked is whether or not this large integer point is the largest integer point on this elliptic curve of relatively small height. And so first of all, one should notice that this is a very special case of this family of elliptic curves. And it's nice to look at things as polynomials sometimes, because polynomials factor, visually factor in a very, very nice way oftentimes. So here we are, we actually have a factor x minus 2, right? So we factor this polynomial. So in other words, this family of cubic polynomials defines, they all define elliptic curves with a 2 torsion point, right? That's really what this is all about. And things oftentimes like computing the rank of a curve and other things like that become quite a bit easier. So here, I'm going to just look at my family of curves that you get after this so-called shift from x minus 2 to x. And Zagier's curve is the particular case, y squared equals x cubed plus 6x squared plus 39x. Now 39 becomes kind of a special number. So it's a previous curve is a special curve in this family. Zagier's curve is when t is equal to 3 and p is equal to 13. So this is the family of curves that I want to look at, but I need to place restrictions on t and p in order to get the result that can be proved. So the t and the p are odd primes for which t minus p over 2 is also an odd prime, And furthermore, T and P have to be different than 1 mod 8. In that case, there is at most one integral point on this curve, y squared equal to xq plus 2t x squared plus tpx with y bigger than 0, unless the equation x to the fourth minus tp y to the fourth equal to 1 is solvable in positive integers xy. And if that were to happen, there may be as many as 2 solutions, but no more. And so we're back with our quartic equation once again. It rears its head. And so it seems that this condition that I stated relating to this equation only happens in the case d is equal to 39. So I'll just state that as a conjecture for anyone who cares. I can't prove it. I don't know how to prove it, but I'm sure that it's true that this equation is never solvable for 2 primes t and p satisfying the conditions of the theorem, or maybe it may not be solvable for any 2 primes other than 3 and 13. Okay. Now, the proof of this theorem, I'm really running out of time. The proof of this theorem, I'm not going to go through in detail. I'll just mention very quickly, how does one go about solving this equation at all? Well, there are various ways. Obviously, you can use programs on the computer, Magma, Cache, Paris, have the basic ideas are stored in those programs. And there's a proof that came from Chen. This is the same Chen as the Chen-Vouzier theorem. And Thue, they solved this using p-adic analysis and algebraic number theory, which goes back to the work of Skolem. But it's complicated. And in any event, there's a different way to solve Zagier's equation. And first of all, the shift that I talked about earlier, there's a reduction step to a quartic equation. This quartic equation has many cases also, so there's a second reduction step to another quartic equation. And then finally, we can appeal to results that appeared in this talk. And I'll try to do that in 2 minutes. So first notice again that we have x equal 2 as a root. So we do the shift and we get the curve that I defined earlier. And so for this curve, we just factor out the x and notice that the greatest common divisor of x and the cofactor has to divide 39. So for a point other than 0, 0, we get integers u and v satisfying these 2 equations, or 3 equations, I guess. And d is one of these numbers. And out of these 8 cases, 7 of them can be dealt with using elementary methods. That's what I'm saying here, maybe modular arguments or solutions to Pell equations and so on. And the difficult one that remains after looking at those 7 cases is this quartic equation right here. So in the case of that quartic equation, the way we proceed from there is we have v squared equal to this. So we subtract the 3u squared, we eliminate it, and we get 30u to the fourth. And a few reduction steps from there, or just some manipulations, gives you many quartic equations of this form where r and s are coefficients satisfying that their product is about 120. And when you look over all those possibilities, there's really only one difficult case. All of them can be dealt with in relatively simple ways. So this one difficult case, we appeal to the fact that we can rewrite it as a Pell equation with coefficient 39. And in this case, we get that this number 2g squared has to be u sub 2t. The index is even for obvious reasons. And finally, What does that say? That says t sub t and u sub t are both squares. And we've seen before that when that happens, t has to be equal to 1. Okay, so what does that tell us? That this number that we had on our previous slide has to be the square of the fundamental solution. And this gives us our values, g, f, w, u, and so on, v, and finally, x and y are the numbers that come from Zagier. So it's surprising that such a large integer point comes from the square of a small unit. This is kind of interesting. It's very unusual that this happens. And in fact, Zagier's point, it's not even a generator of the Mordell-Weil group. It's twice a generator plus a torsion point. So it's amazing that twice a generator, which has a large denominator plus a torsion point, would give you an integer point. I mean, this kind of thing rarely ever happens. So this is a highly unusual situation. Anyway, that's all I wanted to share. I'm sorry if I went over by 1 minute. Thank you.